chapter 2 is largely about different ways that we can represent molecules more in a shortcut notation. And also it introduces the concept of functional groups, which is a huge thing for this chapter. Okay. So we have many different ways that we can show molecules. Lewis structures shows everything. So a Lewis structure, for example, shows the lone pairs. It shows every single covalent bond. It shows every atom as a label. And then from there, we can get down to what are called partially condensed. So what is a partially condensed doing?
It's condensing the methyl groups.
Yeah, it's showing the hydrogens that are bonded to each carbon individually, right? So instead of drawing all the hydrogens out, we're just saying CH3, OH, what have you here. A condensed structure is usually when you print it out in such a way that everything fits on a single line, although sometimes you'll have to branch things above or below the line depending on the groups that are attached. So for example, this is a condensed structure. Another way I could do a condensed structure right there, if I wanted to do it just a little bit less condensed, would be, oh, let me open that real quick. Hold on, I opened it in the wrong file. Okay, here we are. So another way I could condense this, and it might be a little more clear, would be to write CH3, CH, OH, and you see I've left off one of the CH3s, so I could draw it above, or I could draw it below, either way. Or I could draw it like this. And this last form is usually the way I tend to do it if I'm going to do a condensed structure. One of these two ways, commonly. So you notice the difference here is I'm just explicitly showing that there's a line. Very important to understand here, is this bond between carbon and carbon or carbon and hydrogen?
Carbon and carbon.
Yeah, always understand that even though this line is going to the hydrogens, we always read this as a carbon with 3 hydrogens on it. And eventually we're going to give that a name. We'll call that a methyl group in shortly. Okay, so this carbon is bonded to 3 hydrogens, and that carbon is bonded to a carbon with 1 hydrogen. Okay. And then ultimately we can get that down to a molecular formula. Okay, if you were trying to draw a large molecule with 20 or more atoms, what would be by far the most time consuming to draw?
Lewis.
Yeah, the Lewis. But which structures give you the most information? Also,
The Lewis structure.
yeah, the Lewis still gives you the most information, right? But, you know, so do all the others except, which one gives you the least amount of information?
Molecular.
The molecular formula, right? Because all of the first 3 tell you what? That the molecular formula does not tell you.
Or certain molecules are bonded.
Yeah, it's telling you which atoms are connected to which, right? The Lewis structure makes it the most visual. But the partially condensed, I mean, you can still see that pretty well, can't you? Partially condensed, it's still clear that these 3 hydrogens are bonded to that carbon. So given the choice, I would much prefer the partially condensed. In this class, in Chem 120, no way. Because they don't really know how to do all that yet. They're still drawing Lewis structures. Not saying there's anything wrong. It's just you guys have been doing this longer. The condensed structure is still okay, but it might start getting confusing. It's a little harder to see in your head, but it still tells you all this information. It still tells you what atoms are connected to which. The molecular formula doesn't tell me anything except what? When would I want the molecular formula? I would definitely want this if I'm trying to find the molar mass, okay? Or if I was balancing an equation, molecular formulas are great for that. Because that gives you the information right there for that kind of stuff. But it's not going to tell you anything about connection of atoms. Constitutional isomers have the same molecular formula, so you don't need to know the structure if you just want to know the mass, do you? All you need to know is what atoms there are. And so that's useful for just finding that. Okay. So we have, it turns out, 3 isomers of propanol. So this compound here was isopropanol, right? It's this one, same thing as that, propanol, ethyl, methyl, ether. Given that we have 3 ones, which of the structures will represent only isopropanol and not its isomers? So in other words, if I use a Lewis structure, it's clear that I'm talking about isopropanol. If I use partially condensed, it's clear. If I use a condensed structure, is it still clear?
Yes.
Yeah, maybe not quite as quickly, but it's still clear. So all of them are clear except for the molecular formula.
Could the condensed structure be unclear? I mean, I feel like if it was a different molecule, it wouldn't be.
Well, this is good. Let's actually, we'll be practicing. How would it look for propanol? For propanol, it would look like this. CH3, CH2, CH2, OH. Okay, so I mean, there's clearly a difference there, right? 2 CH2s, no CH, in terms of the way you do this. And again, there's more than one way to do a condensed structure. So the key thing to understand is you list carbons and then all the hydrogens bonded to it next. Then the next carbon and all the hydrogens bonded to it next. You do the same thing for every element except hydrogen. So if there was a nitrogen, you could say NH2 and then what's bonded to it next, etc. How do you think, there's not, unfortunately, a consistent way. If there was a way I could say always do it this step and then next step, then I would, but it's something you just kind of figure out as you go. So this would be what? How would we do this one? So the first C would be C.
CH3.
CH3.
Good.
Parentheses.
2.
You don't need a parentheses.
But you have 2 at the beginning and at the end.
Wait, on this one?
Yeah, on that one.
No,
So you
but they're not bonded to the same carbon.
Oh. So
Right.
you have to separate them?
Oh, definitely. Yeah.
All right.
CH3,
Thank you.
CH2, then
CH3.
no, O,
O.
CH3. And if you don't like it that way, this might be easier. CH3, CH2, O, CH3. Because if you draw the line, it makes it more explicit that that O is bonded to each of those carbons. Okay. Good. Let me give you another one just for practice. Let's see, what's this? Oh, this is just me doodling. Okay, so away goes the doodles. All right, how about this one? Let me change that. Hold on. Let's try that one. Or better yet, there we go. So that's a simplification, because what did I do to all those hydrogens?
Just made the methyls.
Yeah, CH3s, good.
Would it be CH3 parentheses 4C?
That's one way to do it. So you could do it this way. This would be the shortest way possible. Because that one carbon has that, or CH3, 4. Oops. Either of these would be understood the same. Okay. Right? So that's one carbon bonded to 4 CH3s. That works fine. I don't generally like it as much. How about this? I would be more inclined to write this as CH3, C, CH3, CH3, CH3. That's usually how I would do it. Or we could do CH3, C, CH3, 3. Those all work. Okay. So in other words, there's not one, only one. All of these should be telling me I have a CH3 bonded to a carbon with 3 more CH3s on them. Or I have one carbon bonded to 4 CH3s. Okay. All of those work fine. But what atom is really littering everything up? The big mess is all those hydrogens, right? The important thing to focus on is going to be this. Because I know full well, in almost all cases, carbon has an octet, right? I also know what? Carbon makes how many bonds? 4. So if carbon makes 4 bonds, every bond that I see counts as 1. So this carbon makes 4 bonds, right? No problem there. It's fine. It's got its octet. No issue. All of these, how many bonds are being shown? Only 1. So that means there must be 3 more bonds that I'm not showing, which would be hydrogens. Okay. So we're going to come up with a shortcut notation that's even more of a shortcut than this. And that's how we're going to generally represent molecules. Okay. And that is what we call bond line structures. people give these things all kinds of different names. Okay, so this is amoxicillin. I'm sure you've all been prescribed amoxicillin before, right? That is probably the antibiotic of choice. It's a mess when you have all the hydrogens drawn in, okay? The bond line structure to the right is much easier to draw. It is much cleaner. And once you know what you're doing, it's much easier to interpret. Okay. So let's see if we can kind of figure out what's there and what's gone. What are the most obvious things that are gone as we go from left to right?
Hydrogens.
Yeah. Are all hydrogens gone?
No,
Which hydrogens seem to have been left?
just the ones that are with the groups, like the OH and the NH2.
Yeah, anything other than carbon. That's the important thing, right? So there's hydrogens on each of these, but they were all gone. What else is gone?
The carbons.
What's that?
The carbons are gone.
Yes, the carbon labels are gone. That's the important thing. The carbon labels have been replaced by intersections. Wherever a point intersects, that is a carbon. So this is a carbon right here. And this is a carbon right here. This is not a carbon. This is a nitrogen. This is a carbon right here. And this is a carbon. And also endpoints are carbons. So that is a carbon. And that's a carbon. Okay. Double bonds are drawn as 2 lines. So instead of focusing on the carbon labels, what are we focusing on instead? We're focusing not on the atoms, we're focusing on the bonds. Okay. So we pretty much got rid of the C's and we drew only the bonds, if that makes sense. Okay. So it first seems kind of weird, as I said, because many of the atoms are not labeled. Okay. But this is usually how we're going to do it. So let's see if we can kind of come up then with just a nice typical way of doing this. Okay. So the first thing is, just like Lewis structures, we draw lines to represent the bonds. And we draw the bonds usually at zigzags. Okay. So, for example, this structure right here is a carbon, a carbon, a carbon, a carbon, a carbon, a carbon. How many carbons total does this structure represent?
7.
6. Right? 6. Yeah. So an endpoint is a carbon, and any point where 2 lines meet is a carbon. And then the lines stand for the covalent bonds. Okay, the bonds in between them. Okay. What is the hybridization of each one of these carbons? They all have 4 atoms on them, and they're only making single bonds, so they're all sp3. So what is the angle? Even though we're zigzagging, what is the angle here?
109.
Yeah, 109.5. Okay. So a carbon is at every intersection or endpoint. We omit carbon-hydrogen bonds. Why? Well, kind of because we can, but largely it's because they are clogging up space. So if we don't show them, how do we know how many are on a carbon? Remember, the rule is carbon makes 4 bonds. Any bond that is not shown is to a hydrogen. Okay. So that's the key thing to understand there. Okay. So any bonds which are not shown are to a hydrogen. So that's the key logic. So any carbon shown with less than 4 bonds must have enough hydrogens bonded to it to reach a total of 4. Good. Okay. So if I look at this, this is a C with 3 hydrogens, right? What is this right here?
A C with 2 hydrogens.
Yeah, C with 2. How about this and this and this?
CH2.
Yeah, those have 2 hydrogens. And then here would be a
CH3.
CH3. Good. How about this one? Let me draw this as a condensed structure. So this would be, let's see here. So this will be a CH3. When you're first learning it, maybe it's easier just to draw in hydrogens like that. So now there's 4 bonds. How many hydrogens would be on this carbon right here?
Just 1.
1. Good. I'll just draw a little blue line there. This one at the top? 3, right? How about the other one way over at the end right here? Also 3. Yeah, good. And then these guys in the middle, each one has 2, right? So as a condensed structure, I could write CH3, C with 1 H, another CH3, CH2, CH2, CH3.
And all the bond angles for these would be 109 too.
Everything in this
Carbon,
whole
right?
line right here is 109.5. Everything is 109.5 or very close.
Because it's at sp3, right?
Yeah, they're all the carbons are sp3.
All right. But if there was like a double bond, then it'd switch it up, right?
Yeah, exactly. Double bond would typically be sp2, unless it's 2 double bonds, and that would be sp. Okay, same idea here. When you're first getting used to this, there's 3 hydrogens, right? 1 hydrogen, 1 hydrogen, 3, 3. Because carbon must make 4 bonds. Good. So if I wanted to really shorten this one up, I could say CH3, 2, CH, CH, CH3, 2. There's going to be a word for these kinds of compounds. First of all, the most general word is hydrocarbon. Hydrocarbon means only contains carbon and hydrogen, okay? And these are going to be called alkanes because the carbons only have single bonds. We'll get that word a little while later today. Okay, so all of these, because there's only single bonds, they're all 109.5 degree angles. They're all sp3, all the carbons. With a double bond, we still draw it the same way, although it's understood now, even though we're drawing it the same, what is the bond angle now, technically?
120.
120, yeah. We know it is, even though we're not going to get out a protractor and measure it each time. The only one we are careful with is with triple bonds, because triple bonds are linear, right? They're sp hybridized. Be very careful about this. So you don't want to do it like this, incorrect, where you're angling a triple bond. A triple bond doesn't get angled. Remember, this is the same as CH3, C triple bond, CH3. Remember, the end of a point is always a carbon. It is not a hydrogen. Another note. Is you can draw add the hydrogens if you want. The key is they are just optional. And usually left out. So the only time you would draw them in is if you want to call attention to them or make sure you don't forget about them, okay? So some people might look at this and go, oh, you know, there's just, they might forget that there's a hydrogen there. How do we know there has to be a hydrogen here?
Because there's only 3 bonds.
Only 3 bonds, good. So we see a bond and a double bond, that's 3 bonds. So there must be a hydrogen here. Same thing here. So just because I say we leave them out doesn't mean they have to be left out. You may draw them in if you wish. Okay. Any questions so far on these guys? Okay. Now, ultimately then, remember, as I said, this is just kind of reinforcing here. This is the way that we would usually do it. This is the book's way of saying we're calling attention to this carbon, the way they've drawn that little box around there. But we can do it like this if we really wanted to draw out all the hydrogens. So the real goal for the next couple days is to get into your head that you can see this picture the same as this picture, that you can quickly say CH3, C, CH2, CH2, CH3, that you can see all the hydrogens. And it's just a matter of learning patterns after a while. Oh no, I might need to reprint some of these. I'm not sure why these labels are doing that. Okay. Let me skip to another point real quick, and then I'll go back to what I just missed. So the bottom of page 20. Heteroatoms is any atom other than carbon and hydrogen. So the 2 most common heteroatoms are in organic chemistry?
Oxygen and nitrogen.
Oxygen and nitrogen. Very good. Good. So heteroatoms, you must draw the labels. And any hydrogens on heteroatoms, you do need to draw the hydrogen. Okay? You may not leave off of a hydrogen that's bonded to oxygen or nitrogen or anything other than carbon. Okay? You do not have to draw lone pairs, but they are often recommended.
You said the most common heteroatoms were oxygen and nitrogen?
Oxygen and nitrogen, yeah. And then after that would be sulfur and the halogens. Okay. I would say omit these when you're comfortable. Once you can be sure that you see them, then you're fine. Remember, what's the pattern? Carbon usually makes 4 bonds, no lone pairs. Nitrogen makes 3 bonds,
1 lone pair,
oxygen, 2 bonds, 2
2
lone
pairs.
Yeah. So after a while, like if you had to draw, 6 chlorines, it would be a real pain to draw in all the lone pairs. So after a while, you start just leaving them off. Okay. How many carbon atoms are there in this structure? How many carbon atoms? So let's go through and make a dot. So whenever a line goes straight to an S, there's no carbon in between, okay? So this is just an S. So here we have 1 carbon, 2. Be very careful with the triple bond. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we've got 15. How about hydrogens? So we've got, let's not mess up our counting here. 1, 2, 3. None here, right? You can see my arrow? Yeah. None here. How about here?
Just 1.
There's 1 there. Good. Because there has to be a total of 4 bonds. Good. So 1, 2, 3, 4. How about here?
None.
None. How about above?
3.
3.
5, 6, 7. Good. Let's do all the methyls, all the ones at the ends. 8, 9, 10, 11, 12, 13, 14, 15, 16. Can we agree that there are none here?
Yes.
None here?
Yes.
How about here?
1.
1. Good. So 17. Where else? How about here? How many there?
2.
2 more, right? So 18, 19, and I think that's it. Good. And then the rest of the formula would be CLS. Knowing the order of those, by the way, is not easy. It would have to be memorized, and I don't even know that. It's really bizarre. It's carbon, then hydrogen, then it's like you almost have to know the order in which they're most likely to comment a molecule. So don't worry about SCl or L or CLS. The key is 15 carbons, 19 hydrogens, right? Good. Let's do lone pairs. Where do I need lone pairs?
Cl.
The Cl needs how many?
3 lone pairs.
Good. 1, 2, 3. Anyone else need lone pairs?
Sulfur.
Sulfur should have
2.
2. Sulfur is like oxygen. It's right below it in the periodic table. Good. How many pi bonds are there? We only need to look at double and triple, right? Each triple has how many pi bonds? A double bond has 1 pi bond and a triple has 2. So we've got 2 pi bonds there. We've got 1 here, 1 here, 1 here. So a total of 5 pi bonds. Any questions? Again, the important thing is hydrogens bonded to the heteroatoms must be drawn. Good. By the way, why zigzags? If we didn't zigzag, what would it look like?
A giant line.
Yeah. And the giant line has how many carbons on it? No idea, right? So you zigzag to the maximum extent possible. Sometimes it's not convenient, and you might have to come up with other ways of, you don't always have to match 109.5 because you might run out of space, but you want to try to follow it as quickly, as easily as you can. The other thing is, please, this is what makes me cry when I look at structures. Follow VSEPR. VSEPR says you want to spread out the electron pairs, right? So this is much better looking than this. This is really ugly, okay? Because look at this whole big space up here that was just left totally blank. So the idea generally is whenever there's 2 groups, that's good. Whenever there's 3 groups, try to draw them kind of like that Mercedes-Benz symbol, regardless of what the angle is, okay? That's usually the way you want to do it. And 4 groups would usually be like this. And sometimes you make those 2 groups a little closer to each other. It depends. But you want to usually draw them out. Or even a cross. I just don't like crosses in my structures because they look too much like 90-degree angles. So usually something like this is better. Anyway, let me get rid of these because they're not very well done. Now here is where people really start having a hard time. You can always rotate a single bond. Single bonds rotate totally freely. So if I rotate this bond, this group right here can swing from there down to there. So this is the same thing. Same idea over here. If I swing this bond in, then this can become this. Or I could even draw it like this. Those are all the same. Because the key thing is you have to be able to look at it and say, I have a CH3, a CH2, a CH, okay, CH3, CH2, CH, bonded to a CH3, bonded to a CH3, CH2, CH2, CH3, CH3. Different rotations produce things called conformations, and that will be a big issue in chapter 4. But they're the same chemical because you haven't broken any bonds. You have just turned atoms around in space. Okay. How else could I do this one? Well, how about like this? Down, So how many do I have? 1, 2, 3, 4, 5. So that's the same as this. Those are all the same thing, which is the same as this. All I've done is twist the bonds. Sometimes I zig left, sometimes I zig right, sometimes I zig up, sometimes I zig down, but the key is it's still the same. And this is what really takes practice in recognizing that these are the same. And when we get into chapter 4, we will name them and we will find that they all have the same name. So if they all have the same name, they must be the same chemical. Okay, any issues with this? Any questions about that? No? Okay. Oh, these structures did not print out nicely. Maybe I need to print out this group again. Okay. Can you see this decently? If not, I will put it up on the screen. There, that's a little bit better. So you'll notice this bottom one is just horrible because why? It's just a mess with all of the hydrogens, right? So it would be much easier to represent this as bond line drawings. Would you try that, please? So take these two and redraw them. Are we all going to probably get the same answer? Probably not exactly, but maybe close.
Can double bonds be linear? Can we write them straight?
No, double
No.
bonds should not be linear. Double bonds should always be zagged. Unless there's two of them.
Like for
same
the
carbon.
bottom one, like starting it off.
Yeah.
So we can write it linear then.
Yeah, in other words, you should usually not do them linear. And God, my drawing is so bad here. You cannot see my drawings yet, right? Because I think I have you paused.
No.
No.
Good, then I'll cheat. And I'll use my software to do it. Okay. So something like this would work for the first one. Yeah, this is nice for the second one. When I did this by hand, they weren't so bad. They could have looked better though. The problem is getting used to this tablet doesn't have much friction, so it's easier to do by pencil or pen than electronically. Okay, any questions about these guys here? I know it's hard to ask. You're saying that, we'll have to point or whatever. But any questions about these guys? And remember, these could be, if you take a look here, they could be rotated. That's totally fine. They could be flipped. That's totally fine. I asked the computer to clean it up. That's another way of doing it right there. These are all the same thing, just different ways of drawing them out. Okay. All right. This software is obscenely expensive. It's, I think, about, I want to say, I think at last check, it's like, I think $1,800 to $2,000 a license. There is free software that does it though. So, and there's ways you can do it just on the internet without even downloading software that I'll recommend. The reason it's so expensive is because it also does all these other things of which I don't even need 95% of them, which is why I always argue, it's like, well, we don't really need to spend all that much money. I mean, considering I need 5% of what that software provides. Anyway, let's see here. 3 possible isomers with this formula here. Let me give you a hint. This must contain a double bond or a ring. Okay. There must be a double bond or a ring, not both, and no triple bonds. There's no way to do it otherwise. Where did I come up with that? If you remember in the first homework, in the homework assignments I was talking about, Let me find that again. This formula tells me that. How many carbons were there in that formula?
9. Oh, carbons?
5, right?
5, yeah.
So I'll just show you. So number of carbons is 5. So 2 times 5 plus 2 is 12. How many hydrogens? 9, right? So 12 minus 9 is 3, plus how many nitrogens? 0. Minus how many halogens is 1 halogen, so minus 1 is 2, right? So 2 divided by 2 is 1. That means 1 pi bond, or 1 ring. Okay, so it's a useful formula when you're trying to draw these things really quickly. Okay, 1 pi bond or 1 ring. So I'll do one with you. Probably the easiest way to go would be 5 carbons, just do your 5 carbons in a line. Let's put an O here. Let's put a chlorine somewhere. About right there. And maybe I'll make this a double bond. So there's my double bond. And usually we draw in a hydrogen in that group right there. Not required, but usually we do. So I'll draw in that hydrogen. Let's make sure this works. How many hydrogens? So here there are 3 plus 2 is 5 plus 1 is 6 plus
Another 2.
2 is 8 plus 1 is 9. It really is awful when people blow 10 to 20 points on the first exam because they drew all the things and they didn't have the right number of hydrogens. Always check. If this has 9 hydrogens, 9 hydrogens. So 3 plus 2 plus 1 plus 2 plus 1 would be there. Okay.
Why exactly did you draw in the H, the hydrogen?
It's not required. It's just common. When this is sp2, we usually do. It's not required. If you left it off, that would be totally acceptable. Okay. So part of it's just personal obsession. You know, I don't like to leave off a hydrogen. This is going to be called an aldehyde. We'll talk about that very shortly. And we usually leave them on hydrogens for aldehydes. How could I easily change this? What would be one easy way to change this to the least amount of effort possible?
Flip the Cl and the O.
Put the Cl just anywhere else, right? So like, how about here? That would be one, right? How about I said, I want you to do one where there's no double bond between O and H. I mean, between O and carbon. Then where's the only other place there could be a double bonds? Between what other atoms? It'd have to be between carbon and carbon, right? Chlorine, remember, in organic compounds generally only makes a single bond. So how about this? 1, 2, 3, 4, 5. What would this be now instead of, oops, hold on. Good. I can't just leave it as an O. It would be O, H, and maybe I'll just put a chlorine over there. There are so many ways you could do this. I've only done carbons in chains. Maybe I don't need carbons in chains. Maybe I could do a branch. There's another one. 1, 2, 3, 4. Oops. 1, 2, 3, 4, 5. Too many atoms. How about this? That works. 1, 2, 3, 4. No, still doesn't work. I keep drawing an extra carbon. There we go. That works. That's a single bond right there. Okay. And I can even draw ones with rings. There's many, 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 many ways you could do this one.
Would you be able to put the O in the middle?
Yes. So tell me what to do. Here's an O.
Like 2 carbons on the side.
On each side, one on each.
Yeah. And then a double bond somewhere.
Like, how's this? Okay, so I've got 1, 2, O, 3, 4, 5. That works. I didn't draw it very nicely, but 1, 2, 3, 4, 5. That works. Double check. That has 2 hydrogens, 3 hydrogens, 4, 5, 6, 7, 8, 9. Yeah. That works. Totally different. That's why I like giving questions like this, because again, there's so many. You're not likely to draw the same one twice. Although sometimes it's amazing to me. There might be 25 possibilities and someone draws the same 3. It's just 3 different ways. Okay, yeah. These are definitely different. Good. 3 different rotational conformations. Translation means same compound drawn different ways. So in other words, not isomers. So what have we got? CH2CH. There we go. That works. Oh, wait. This is an error. Sorry. CH3. CH3CH. No? Hold on. I don't think that's right. CH3CH. I need to change that. That doesn't make any sense. Okay, let's make that CH3. CH, that's not even right there. You know what, let's just get rid of that question, please. Yeah. Yeah, that's not well drawn. So just get rid of that, please. I'll come up with something else. Okay. Functional groups. This is probably the big topic of the day. Well, drawing molecules and functional groups. So this is going to have a lot of memorization involved, unfortunately. So we like to do it this way because it allows us to quickly predict how a chemical reaction has changed a molecule. For example, if I look at these two ways of drawing the same reaction, I think it's really quick to see that where is it easier to notice the change? Well, I mean, they're both pretty easy. But to me, I think it's very quick to see that that double bond has changed into a single bond, right? Yeah, this double bond has changed into a single bond. What this is just telling me is I've taken this chemical, I've added hydrogen to it over platinum to speed up the reaction. What do we call that if something is speeding up the reaction but not used up?
Catalyst.
Yeah, good. So that's a platinum catalyst, and that gets rid of the double bond. Good. So they both kind of work, but in many cases, condensed structures just, it's really hard to figure out what happened. Line drawings make it really easy to see. There's definitely a change there. Our eyes jump right to it. Okay. So there are certain combinations of atoms that can be combined in different relationships, and these give us what are going to be called different functional groups. They are called functional because they basically, the function tells you how they are going to behave in reactions. For example, this double bond, a lot of compounds with carbon-carbon double bonds, if you add hydrogen and platinum, the double bond becomes a single bond. So I don't have to memorize 8 million different reactions. I just have to know that whenever I add hydrogen to a carbon-carbon double bond, it will become a carbon-carbon single bond. Where did the hydrogens go, by the way? How many hydrogens are here right now?
One.
One. And how many in the product?
Two.
Two. So I added one hydrogen to that side. And what about over here? How many hydrogens are there here?
None.
0. And now there are
1.
Okay. Good. So once I learn this pattern, I can do it for all kinds of these. This kind of a compound is called an alkene. Okay. So the first groups that we're going to look at, and these are all in table 2.1 of your book, are these three right here are called, oops, well, no, it's not divided the way I would want to do it normally. But these two right here are called hydrocarbons. They only contain carbon and hydrogen. They are alkenes and alkynes. Okay, so an alkene is when you have a carbon-carbon double bond. An alkyne is when you have a carbon-carbon triple bond. It doesn't matter what it's attached to. The only thing that's important is that there's a carbon-carbon triple bond. You'll notice that we're listing this in the order that we cover them in each chapter. They're very rich in terms of the number of reactions these guys undergo. I've got to make sure that this is, I think this is the same as for the new book. They moved this around a bit in the old book. Okay, so just use whatever chapter numbers are there. You don't need to memorize which chapter goes with it. Alkyl halides. Alkyl halides are whenever you have a carbon bonded to a halogen. Chlorine, bromine, iodine, or fluorine. We're just not going to worry about fluorine much. Fluorine doesn't behave as well. The other word you could use instead of alkyl halide would be alkyl chloride if it's chlorine, alkyl bromide if it's bromine. So that's just more specific. Alkyl iodide if it's iodine. But generally, we just use the phrase alkyl halide. A word I'm sure you're familiar with is alcohol. Alcohol is when you have carbon bonded to OH with certain important exceptions. And I'll call out those exceptions in a moment. The rule usually is that this carbon has to be sp3. But we'll see that in a moment in more detail. So there's an alcohol. Okay. An ether is when you get an oxygen with a carbon on each side. Let me be very clear about this R thing, okay? R. R means any carbon group, usually. So it could be a CH3, it could be CH3CH2, it could be a ring. It's just, R is just standing in for carbon groups, okay? The most common carbon groups are, if we were to go back to the notes from chapter 1, in the what's it called, on the table of contents, I gave a bunch of these guys right here. Methyl, ethyl, propyl. We'll worry about their names later, but these are all common R groups. So in other words, it could be this or this or this. The key is it's just carbons and hydrogens. Okay. Sometimes R can also mean hydrogen by itself, but we're not going to assume that right now. Okay, so for example, the most common of all of the ethers is diethyl ether. So what is R standing for here? It's standing for CH3, CH2. It's like an X in algebra. Okay. So ethers are bridges between two carbons. Thiols are the same as alcohols except what?
Sulfur.
Yeah, good. Thio pretty much always means change oxygen to sulfur. Thio means change oxygen to sulfur. So alcohol, thiol, OL, they both end in ol. So oxygen is replaced by sulfur. Good. Those functional groups and their reactions are going to be the root of chemistry 230. So the first 6 chapters are about theory. The next chapters are about reactivity, and that takes us through there. But you need to know all the functional groups. Okay. Aromatics. Aromatics, we're going to define aromatics later, but for right now, I'm going to give you a very simple definition. Anything that contains this group here is called aromatic. This molecule right here is called benzene. Okay, benzene. Anything that contains benzene is aromatic. That is a very common pattern, and we'll see it quite a bit later on. Okay. Ketones and aldehydes are related. The difference is A ketone has a carbon-oxygen double bond where the carbon is bonded to 2 carbons versus an aldehyde where the carbon is bonded to at least 1 hydrogen. There is one aldehyde where you have a hydrogen on both sides. There can only be one where there's a hydrogen on both sides. And that one's called formaldehyde. Have you all heard of formaldehyde? So formaldehyde is hydrogen, carbon, double bond, oxygen, hydrogen. The other aldehydes have carbon on this side. Okay. Carboxylic acids. We'll talk about these a lot today in the lab. Carboxylic acids have OH, right? But they are not alcohols. So remember when I said not all carbon OHs were alcohols? This is the very important exception. If there's an OH on this over here, but this carbon has a double bond O, we call it a carboxylic acid. You're already familiar with the most important carboxylic acid, acetic acid. You all heard of acetic acid, right? Acetic acid is when you have CH3 here for the R group. This is pentanoic acid. Good. You don't need to know any of these names now. You will by the end of 231, but not now. And there are more. Where are the rest? Where are you? Oh my. Where are the rest? And how did they get left off? Esters, amides, and amines. All right, let me draw those in real quick. Oh, they're there. They're on your notes, right? Okay. Sulfides. Sulfides somehow got left off. So that's sulfide is the same as what? The same as ether, except you change oxygen to a sulfur. Good. Ketones and aldehydes, carboxylic acid is like this. Acyl halides and anhydrides, these are not as important for right now. So don't worry about these two just yet. Don't worry about them this semester. But these next three are very important. Esters, amides, and amines. An amine is whenever you have a nitrogen bonded to 1, 2, or 3 carbons. 1, 2, or 3 carbons. So, for example, this is an amine also, called methylamine. That's diethylamine. Here's another amine. Okay, these are all amines. And I'll draw in the lone pairs. Amine and amide, what's the difference? An amide is like an amine, except next door is a carbon-oxygen double bond. Okay? That makes the reaction different. The way they react, the way they behave. And that's why they're given different names, different groups. And finally, esters. Esters look a lot like ethers, except what? It's just like an ether, except there's an oxygen-carbon double bond next door. Okay. So your job is that you need to be able to recognize all of these functional groups and name them. Be very careful, again, not to mix up alcohols and carboxylic acids, ethers and esters, amides and amines. Those are the easiest ones to mix up. Because again, amide, ester, and carboxylic acid all have a carbon-oxygen double bond. Okay. This is by no means the whole list. There are many, many, many more, but these are the most important ones by far. I mean, this accounts for about 99% of all organic chemicals. We will also learn about imines and enamines and what else? Oximes and sulfonamides and a whole bunch of other ones. But, you know, for right now, that's the important ones to know. Okay, let's practice, shall we? I'm going to draw several molecules. And I want to find the functional groups. Oops. And then we'll end after this. No, not ChemDraw. Here we are. So I'm going to draw some functional groups here. First, let me do molecules with only one functional group. Very important, by the way. Remember I said there were aromatics, the ones that have benzene rings on them? A benzene ring must have double, single, double, single, double, single. If it doesn't have that pattern, it is not a benzene ring, it is not aromatic. Vitally important. So this is not aromatic. This is just single bonds. Okay. So there's one. Let's see. Okay, let's identify functional groups here. Which atoms usually should draw your eyes? I would usually be drawn to heteroatoms, right? If there are any heteroatoms, meaning oxygen, nitrogen, sulfur, look at those first. Okay, we have an oxygen, OH, bonded to a carbon on the left here. What is that functional group right here?
Alcohol?
That's an alcohol. Very good. If I ask you to label them, I would usually mean draw an arrow to it, but that's the only functional group there. Good. How about here? Probably has to do with the nitrogen. That would be
Amine.
amine. Good, that's an amine. How about this?
Ether.
That's an ether. Good, because the oxygen is bonded to carbon on either side, and there's no carbon-oxygen double bonds anywhere. So this is an ether. This one,
Is that a ketone?
that's a ketone. Very good. Ketone. This one,
Carboxylic acid.
very good. It has an OH, but next door is a carbon-oxygen double bond. That's a carboxylic acid. Okay, no heteroatoms on these next two. Carbon-carbon triple bond. That's called an
Alkyne.
alkyne, yes. Probably the worst bumper sticker I've ever seen is it takes, this is bad chemistry humor, it takes all kinds to make a world. Isn't that nice? You don't get it. Okay, fine. It takes all kinds. Anyway, I feel so bad. I'm just going to get rid of it. All right, go away. Anyway.
I wrote it down.
Yes, it's a really bad chemistry humor. You know. Are you a nucleus? I don't know. How do I know you're a nucleus? Because I'm positive. You know, it's just really.
That was a good one.
Yeah, it's in a cartoon somewhere. I saw that. It's just really bad. How about this? This is aromatic. It's got a benzene ring. One very important term, and then we'll go for a break. And it's important because it'll come up in lab today, and I'll say it again in lab. Oh, by the way, with aromatics, we sometimes draw them like this. You can see my screen, right? With a circle in the middle. Okay. So that's kind of lazy way of doing it. I don't like to do it that way, but you can do that. But let me be very specific about one other type. What two functional groups do we seem to have here?
Aromatic and
Yeah, these get a special name. These are called phenols, and the name of this compound is phenol. Okay. So usually, if you said this was aromatic, I would not say it's wrong. If you said it was an alcohol, I probably would. Aromatic alcohols are called phenols, and the reason this is going to be important is because when we get into the lab today, we'll talk about them. They are acidic. Alcohols are as acidic as water, usually. And how acidic is water? Water is usually considered what? On the acid-base scale?
7.
Yeah, it's neutral, right? It's neutral. So alcohols are neutral, but phenols are weak acids. Okay. By the way, when we start talking in organic chemistry, going, oh, this is such a strong acid, that's still a weak acid. Okay. The strong acids are hydrochloric, hydropropane. The ones you learned last semester, those are still the strong acids. Okay. This is a very, very weak acid. All right. So that's not on the list, but it's a term you should know. Phenol.